All right, so here we are at Module 9, Engine Performance. So we got a lot of cool stuff to cover in this module. Some of the things we're going to talk about is air-fuel mixtures, the engine sensors, all those sensors on the engine. We're going to talk about gasoline properties, and we're also going to talk about some incorrect running conditions. So let's get started. So engine performance. I hate to burst anybody's bubble who thinks this is going to be about making your car go faster, high performance work. Really what we're talking about in this module is engine performance is basically a combination of power output, economy, and durability. So in module 3, we went over understanding engines. And now that you know that, now that you know what it takes to make an engine tick, well, now let's look at how to control that engine and make it a finely tuned machine. Because we don't want our cars to just run, we want them to run perfectly. So let's take a look. So a perfectly running engine will consume the entire amount of both fuel and air it ingests. It'll consume 100% of it. And this perfect mixture of fuel and air is called the stoichiometric mixture. Let me say that again, stoichiometric mixture. Okay, so this mixture will consist of 14.7 parts air to 1 part fuel, or 14.7 to 1. And I don't know who figured this out. Some scientist somewhere decided that the most combustible mixture would be 14.7 parts air to 1 part fuel. Anything less than that does not create the amount of combustion we want. Anything more than that does not create the most efficient combustion or the amount of power by igniting the mixture. So that's called stoichiometric mixture. That's what we're trying to achieve with these engines. Now, something kind of funny about that 14.7 to 1, just remember that number, 14.7, because it's an important number, and it's just ironic, but 14.7 to 1 is also the barometric pressure at sea level. You guys didn't know you're going to be learning all these cool little tips, did you? So 14.7 to 1 at sea level, which is not your local, it's not an inland lake. Sea level refers to the ocean. The amount of barometric pressure at sea level, so ocean level, is 14.7 psi. So there's an interesting fact for you, and I'm going to explain why that number is important, or why we even care about barometric pressure here in a little bit. So rich versus lean, we're going to talk about that. So now if an engine runs with too little fuel, we call that a lean condition. Transversely, if an engine runs with too much fuel, we call that a rich condition. Another way to remember that is, I put this on here, rich equals dirty, lean equals hot. So a lean engine that does not have enough fuel is going to get really hot. It just gets really, really hot. Remember, fuel helps cool engines down, actually, as it enters. It helps cool an engine. If you have too much fuel, we call that a rich condition, and it runs really, really dirty, really sooty. So rich equals dirty, lean equals hot. Just another way to remember it. Okay, so let's talk about obtaining the perfect mixture. So we have an engine. Now, how do we control this engine to make it run at the perfect mixture? Okay, so obtaining the perfect mixture. So how do we do that? How do we control this engine to make it run at the perfect mixture? The answer is a whole crap load of sensors and a computer. Basically, that's what it is. All right, so the computer, or as we've explained it before, the PCM or ECM, powertrain control module or engine control module, is constantly adjusting the fuel mixture and the ignition timing the whole time the vehicle is running. So the whole time you're driving your vehicle, it's constantly calculating and manipulating the fuel curve and the ignition timing curve to obtain this perfect mixture. It's really, if you guys, it's really amazing to think, how far we've come, and that, take it for granted. You're driving your car around and the thing's constantly adjusting itself to make it run perfectly. So it is kind of cool. I always think so. Now remember, and you'll hear me say this 100 times, before we can fix it, we got to know how it works. That's the key to the whole thing. Okay, so let's take a look at these different sensors, what they do and how they work. Okay, so let's back up just a minute and talk about what we learned in Module 8. So before we get overwhelmed with these sensors, let's just put it in perspective. All these sensors do are create a voltage in, voltage out reading. So they do their job and they spit out a voltage back to the PCM. Okay, so let's talk about this one, a mass airflow sensor. Its job is measure the amount of air being drawn into the engine. So we want to know how much air this engine is pulling in or sucking in. Now these sensors are somewhat common to fail. So we're going to keep an eye on these because they do fail. Here's a little tech tip. It is important to clean this sensor during an engine tune-up. So during every engine tune-up, if your vehicle has this sensor, it must be cleaned, because the problem is they get dirt build up on them, and then the readings start to go down and down and down. One other thing, since we're talking about it, is if you ever have a vehicle with a K&N air filter, it's like a performance K&N air filter. Well, those things have an oil coating on them. They're oiled. They're supposed to be a performance filter, but what we see is that the oil travels through the intake boot and builds up on these little tiny wire elements here, and then all the dirt and debris, the dirt and dust will just get stuck to that. That makes it through the filter, will get stuck to that. So especially when you guys see a K&N air filter, the first thing that always pops into my mind is, I bet that mass airflow is dirty, no matter what the vehicle comes in for. So there's that. So most vehicles do use mass airflow sensors, but some do not. One that comes to my mind is Chrysler. They do not use a mass airflow sensor. Instead, they use a MAP sensor, which we're going to get to. Now here is a really cool tip for you guys. Make sure to write this down, highlight it, circle it, put a star next to it, because when you're watching your scanner to diagnose a runnability issue, always look at that mass airflow sensor. And just a rule of thumb, you can look it up usually per vehicle. This vehicle should be approximately this much at idle or approximately this much at wide open throttle. And I'm going to talk about grams per second here. GS is grams per second. That's what the computer calculates the output. Remember, voltage in, voltage out. The output that goes to the computer, it calculates that as grams per second. So as a rule of thumb, at 500 RPMs, a mass airflow sensor should read 1 gram per second per liter of engine displacement. So I'm going to say that again. At 500 RPMs, we should be getting 1 gram per second per liter of engine displacement. So for an example, we have a 3-liter engine here, right? 3-liter engine at 500 RPMs should make how many grams per second? 3. Okay, so I put on here, example, a 3-liter engine should have approximately 3 to 5 grams per second at idle. Now why 3 to 5? That is because your engine, typically an engine idles a little bit higher than 500 RPMs. So assuming the engine idle speed is around 600 to 700 RPMs, that's why we give ourselves a little bit more. It's going to be running a little bit faster than 500 RPMs, thus pulling in a little bit more air. So I'm scrolling through the scanner. I got a 3-liter engine. I'm like, okay, let's look at this mass airflow sensor. I got about 4 grams per second. Bingo, that's right where I want it to be. It's a 3-liter engine, so I figure it's going to make about 3 grams per second at idle. Makes 4 because it's idling, say it's idling at 600 RPMs, 700 RPMs. So I know that's right where we want it to be. Okay, another tech tip is if your mass airflow sensor reading is too low, before you do anything else, check for any intake leaks. Because maybe the air is getting in elsewhere. So maybe the air is getting sucked in somewhere post mass airflow sensor or somewhere behind the mass airflow sensor. So always look at the rubber air intake boot between the mass airflow sensor and the intake. Also, we want to look for any vacuum leaks coming from the intake itself, because that could be air is getting drawn in and not going through the sensor, which would give us a low reading, right? Okay, so manifold absolute pressure sensors, or MAP sensors. They measure the amount of vacuum inside the intake manifold. So it measures that amount of vacuum. It calculates that in inches of hydrogen or inches of mercury, and it shows up as INHG on the scanner. Okay, so MAP sensors, just giving you a little heads up here, they don't seem to fail very often. The couple times that I have seen them fail, it's actually been because if we would turn this and look inside, there's a little hole right here for air to go through so it can measure vacuum. I've seen those things actually soot up and completely clog shut, but for the most part, they don't fail very often. Tech tip, the best way to check its accuracy is with your scanner. You're looking at your scanner, key on, engine off. KOEO. In the automotive field, that means key on, engine off. The MAP sensor should match the barometric pressure sensor. So key on, engine off, you're going to see those two sensors match or be really close to it. So that brings us to the barometric pressure sensor. It's pretty much the same part. It does the same thing, really. It measures pressure. This sensor is made to measure atmospheric pressure sensor to make air fuel adjustments. And really its job is it keeps the engine running good at different elevations. So if you're up in the mountains or whether you're down in a big valley, it's still going to keep your engine running correctly. So the higher you go up in the mountains, the lower amount of atmospheric pressure we have. So we need to adjust for that. So that sensor is constantly reading. So if you've ever gone on a road trip and gone up in your mountains, your engine's making massive amounts of adjustments to run perfectly. If you had a carbureted engine, you're going to notice a really large difference from sea level to being at a mountain elevation. You're going to lose performance. It's not going to run right. So that's what this sensor is here for. And remember, at sea level, we have 14.7 psi, which is our magic number. Okay, so let me just pause for a second and tell you guys that we're touching on the main sensors or the key sensors. You might see certain vehicles that have, additional sensors to these, and there are other sensors, but we're going to talk about just the ones that really matter to us right now. So, ambient air temperature sensor. What this thing does is it measures outside air temp. So if you're looking at it in the scanner, it should nearly match the actual outside air temp. So if it's 70 degrees outside, the ambient air temp sensor should be real close to 70 degrees. So it's usually mounted somewhere, away from the engine heat, like in the grill or somewhere even in the front bumper area. And guys, these sensors really don't fail very often. Honestly, the only time I really see these things fail is if we have a front end collision and they get cracked. Otherwise, they really don't fail very often. Okay, now sometimes these sensors are actually incorporated into the mass airflow sensor. And when that happens, this reading is referred to as intake air temp sensor. So sometimes they just incorporate it right into the mass airflow. And again, they call that an intake air temp. So it measures the incoming air instead of measuring just the barometric temperature. So basically, guys, these sensors are measuring the air temp because if it's super cold out, your air is actually denser. And if it's super hot out, the air is actually thinner. So this sensor tells the computer basically what to expect. So we're going to talk about oxygen sensors now, or O2 sensors. And these things are a little bit tricky, a little bit complicated, but we're going to make it easy for you, right? So an O2 sensor or an oxygen sensor measures the amount of oxygen and or unburned fuel in the exhaust gases. Okay, so it tells us if our fuel is getting burned or not burned in the exhaust, or how much of it, I should say, how much of it is getting burned. Now there is a built-in heater inside these sensors, a built-in heating circuit. These sensors don't read unless they're warm. They don't read correctly unless they're really warm or hot. And the exhaust keeps them hot, but there's a sensor built in to help these things warm up actually quicker. Now that being said, as you turn your car on, as things start to warm up, the ECM actually doesn't care what the O2 sensors say for the first 2 to 5 minutes. It doesn't care. It calls that open loop because a cold sensor, a cold O2 sensor, is not going to be accurate. Okay, so they tell the computer for the first 2 to 5 minutes, we don't even care what the O2 sensors say. So it's going to use a predetermined air-fuel mixture, or it's going to use a predetermined O2 sensor reading. You know, it's going to put it like halfway between rich and lean just to get the engine running to warm it up. We call that open loop. So open loop means the engine does not care what the O2 sensors say. It does not care. Okay, so but as soon as this engine does warm up, the O2 sensors switch to what's called closed loop. And now the O2 sensors are being used by the ECM to calculate the air-fuel ratio. So when they go to closed loop, now these sensors are extremely important in making that air-fuel ratio. In fact, I would say they are the most important sensor in calculating the amount of fuel the engine gets. So we call that closed loop. A way to think of that is, I always try to remember that as like an electrical circuit. So pretend you have a loop, or pretend you have a circle of wire. Okay, when that circle is closed, it should be working, right? Or say you have a circle between the positive and negative, whatever you want. When that circuit is open, it's not going to work. You cut the wire, now you have an open circuit, nothing's going to work. You connect the wire together, you have a closed circuit, now it's going to work. Maybe that makes sense to you, maybe it doesn't. All right, so these sensors, most oxygen sensors read in millivolts. So they read on a 0 to 999 millivolt scale. Basically, that's a 0 to 1 volt, but we watch it in millivolts because it's really minute readings. 0 in our scale between 0 to 999, 0 is full lean and 999 is full rich. So on your scanner, you can see what they're reading at. 0 is going to be lean, 999 is going to be rich. Okay, there are O2 sensors that are used before and after the catalytic converter. They are referred to as pre and post cat sensors. They are also referred to as upstream or downstream sensors, which makes sense. Upstream is going to be closer to the engine, downstream is going to be further away from the engine. They are also classified as number 1 and number 2, number 1 being upstream. Kind of confusing, but let me explain. Example, you're going to hear somebody say bank 1 sensor 2, O2 sensor. So what in the world does that mean? So that refers to the downstream sensor on the number 1 bank. Okay, so bank 1 is what B1 stands for, bank 1. And now on an engine that has, a V6 or a V8, they consider that engine to have 2 banks. It's going to have 1 bank on the driver's side and 1 bank on the passenger side, or on a transversely mounted engine, it's going to have 1 bank in the front, 1 bank in the rear. On an inline engine like an inline 4 or an inline 6, it's only going to be bank 1 because there's really only one bank. Okay, so bank 1, sensor 2. Okay, so we know that sensor 2 refers to downstream. Okay, so bank 1, sensor 2. So we know that sensor, they're talking about bank 1. So which one's bank 1? Bank 1 is always going to be which cylinder is always going to correlate with cylinder number 1. So if you ever want to know which bank is which, you got to find your cylinder identification. And it's going to say, like for example, it's going to say, okay, your GM engine, this such and such engine, 5.3 liter engine, cylinder 1 is on the driver's side front, for example, or the left hand front. And you're going to say, okay, so that's cylinder 1. Now we know that is bank 1. So bank 1 will always be housing the number 1 cylinder. Hope that makes sense. So anyways, bank 1, so we know that's the left hand bank. Sensor 2 means it is the downstream O2 sensor or post cat on the left hand bank or driver's side bank. So that's how we refer to those. I know that's kind of confusing, but it'll make sense as you start to figure these things out. Okay, so we got some squiggly lines here and some straight lines. What do these things mean? So a normally running engine will cycle from rich to lean. The pre-cat O2 sensor will cycle. So we have up, down, up, down. This is rich. This is lean. That's what it's designed to do. It cycles rich to lean. So that's a good one. That's what we want the upstream O2 sensor to look like. Okay. Now the post-cat or downstream O2 sensor should look a lot smoother. See how we just got a flat line here? But this is what a good downstream looks like. The reason for that is the catalytic converter. Now remember that catalytic converter glows red hot and it burns off or stabilizes all the unburnt fuel. So when we have a vehicle with a bad catalytic converter, guess what this downstream O2 sensor looks like? The exact same as the upstream. We see it up, down, up, down, up, down. We see it cycling just like the upstream. That's how we diagnose a bad catalytic converter. So anyways, here's an example of a good running engine with a good catalytic converter. We see a nice cycle up and down, pretty even, everything looks good. And we have a flat, even looking post-cat sensor, downstream O2 sensor. Okay, so next we're talking about AF sensors or air fuel ratio sensors. They do the exact same thing as an O2 sensor. Basically, they're just a glorified O2 sensor and they're a lot more expensive. The physical difference is they have fewer holes than an O2 sensor. If we go back a couple slides, you can see that this O2 sensor has a lot of holes right there. So that's how you can physically tell the two apart. So again, airflow sensors are really similar to O2 sensors, but the difference is they read at different values. So why do we need AF sensors? Why aren't O2 sensors good enough? Well, air fuel sensors are a lot more accurate than O2 sensors, and thus becoming more popular due to the strict emissions laws and the super efficient engines. So, you know, as they push and push and push for cleaner running engines and more, fuel economic engines, they've developed these AF sensors that read at just a more accurate scale. And so you're going to see these things more and more often. Now, AF sensors are a little bit harder to diagnose and to monitor and diagnose due to their minute changes. They have a very low milliamp range. All right, so on a perfect running engine, it's going to show the AF sensors at its reference voltage, which is going to also be called lambda. They call lambda the perfect reading. So here's some different examples, different manufacturers have different reference voltages. So I know this is confusing, but pretend your O2 sensor gave you a reading of the stoichiometric mixture, 14.7 to 1, and it basically just went up and down from there. Think of that when we're talking about AF sensors. So basically, our lambda, which is the same as stoichiometric, our lambda, say one manufacturer says it's 1 volt. And so opposite of O2 sensor, during a rich condition, the voltage should decrease, while on a lean condition, the voltage should increase. So our target is 1 volt. If we see the voltage a little bit higher, that means we're lean. If we see the voltage a little bit lower, that means we're rich. 2.6 is another one that other manufacturers use. 2.6 or 3.3 are kind of the common ones that you'll see. Again, it's basically its target voltage, so that's where it wants it to be. Okay, so that was confusing. Let's talk about an easy one here. Coolant temperature sensors. So ECT, engine coolant temp sensor, is constantly measuring the engine coolant, and it reports to the ECM. Now these sensors can and do fail, so always watch these things. Always watch the data pad on the scanner when scrolling through data. These sensors can fail without setting codes. Example, if you notice on your scanner as you're scrolling through it that your engine coolant temp says -40, that's probably incorrect. Unless you live somewhere where I don't ever want to be, that's definitely incorrect. So on our European vehicles, which is Volkswagen, Audi, BMW, to name a few, they're going to read in Celsius. So just do some quick math. You know, Celsius is basically just under half of Fahrenheit. So 200 degrees Fahrenheit equals approximately 90 degrees Celsius. It's not exact, but I mean, we just want to make sure it's not really far off, basically. We want to make sure that it looks close. So one last thing on these sensors. So I've actually seen vehicles come in running full rich, running super rich. They're running really crappy, and you can just smell it that they're running rich. No codes. Guess what I found? A failed coolant temp sensor. It's at -40 degrees, and it's just dumping the fuel at it, right? Because colder air is more dense. So more dense, if we're getting more air, we need more fuel. So just kind of something to watch for. All right, so knock sensors. So this sensor is usually mounted on the engine block or cylinder head. Its job is to measure vibrations caused by engine detonation or pre-ignition. So it basically measures vibrations, and it lets the computer know if the engine has any poor running conditions or dangerous running conditions. So if the knock sensor detects a harmful vibration, pre-ignition, spark knock, it sends a signal to the PCM, which adjusts the ignition timing to compensate for this. So basically it's there to a safety feature to prevent harm from the engine. So if the engine all of a sudden, the knock sensor says, we got something seriously wrong, we got some harmful vibrations, it's the engine's going to most likely retard timing and rich in fuel, put it in sort of a safe mode as to not damage anything. Here's a tech tip though. Most of the time when you get a knock sensor code set in the PCM, it's the sensor itself that's failed. The knock sensor itself is faulty and needs to be replaced. 9 times out of 10, you'll see that the sensor's gone bad. So it's actually really, really rare that you get a knock sensor code for an engine that's actually knocking. In fact, I don't know if I've ever seen it. So, okay, so we're getting there, guys. We're going to talk about a crankshaft position sensor, CKP. So what this thing does is it reads off metal teeth on the crankshaft, telling the ECM telling the computer at what position the crankshaft is at. Most engines will not run without this sensor. So if you unplug this guy, your engine won't start. Tech tip. Guess what? These sensors can fail, And when they do so, they rarely ever set a code. So that's fun. We get a we get a crank no start condition in, yet no codes. That's one of the first things I look for. They can cause a stalling condition or a no start condition when failed. So it is possible that they work intermittently and that they cause the vehicle to stall when they're failing. So another tech tip, so say that vehicle does come in with a no start condition, a crank no start condition. Sometimes you can hook up the scanner and watch engine RPM on the scanner while cranking. So if you're cranking the engine over and you got the scanner hooked up and it's reading 0 RPM, now you might be onto something. This sensor could be a culprit. If you hook up to the computer and you crank it over and it says, okay, I'm cranking at 380 RPM, most likely that sensor's okay. That's just a real quick test. Okay, so just like the engine likes to know where the crankshaft is at all times, it also wants to know where the camshaft is at all times. So the camshaft position sensor basically works the same way as a crankshaft position sensor. So most engines use both a cam position sensor and a crank position sensor. Some engines have more than one, multiple cam position sensors. So when you're watching these things, diagnose them, just remember the camshaft is supposed to spin at half the speed as the crankshaft. Now having these sensors on there also help. So with vehicles that have both crank and cam sensors, that also helps. The computer watches that to make sure that our cam timing is where it needs to be. Okay, throttle position sensors, also known as TPS sensors. They tell the computers the exact position of the throttle blade as you're stepping on the throttle. Usually located right on the throttle body. Okay, so tech tip, there's a quick, easy way to test these things, guys. You go in the scanner, you find TPS sensor on there, key on engine off, so shut the engine off, yet turn the key on, slowly press on the throttle, and look for the sensor to smoothly increase to 100%, nearly 100%. If it starts spiking and jumping around, that's a problem. Okay, we are getting close now. Vehicle speed sensor. So the vehicle speed sensor tells the ECM and TCM how fast the vehicle is moving. There's usually one for the speedo and one for the other computers. So it's not uncommon to have 2, sometimes even 3 speed sensors. Now these things are usually located on the differential on rear-wheel drive vehicles, or on the transmission of a front-wheel drive vehicle, or on the transfer case, or all of the above. Speed sensors. Okay, idle air control motor. So that's a goofy looking thing. An IAC. This thing controls idle speed, and it does so by adjusting the amount of air allowed into the engine with the throttle blade closed. So your throttle blade is closed, right, because your foot is off the throttle. Now your engine, by means of this thing right here, is going to control how much air it lets in to adjust idle. There's usually coolant running through these things. You can see a hose fitting here. You can't really see it, but a hose fitting here. Right there's a coolant passage. Tech tip. My personal experience, I have had horrible luck with these things by using aftermarket parts. So no matter what, in my shop, if we have these things fail, we put a dealer part on. They might be a little bit more expensive, but I have had terrible luck with these things aftermarket. I don't know why, but you put one on and it idles worse than before, or it's doing something really weird. So I don't fool around with aftermarket parts with these. So that's just that's a helpful tip for you. I have learned the hard way. So also these things are usually mounted on the throttle body. Okay, next, oil pressure sensor. Threads right into the engine block or oil filter housing. Okay, it sends a pressure reading for the oil pressure gauge and the PCM. If you are questioning an oil pressure sensor, say it's got low pressure and you're like, I don't know if that sensor's right, easy. Hook up a manual gauge and take out the guesswork. So if you have an engine that's got low oil pressure and you're not sure if it truly does have low oil pressure, or maybe the sensor's reading inaccurately, simplest thing to do, find the sensor, unthread it, and hook up a manual gauge. Now you got manual gauge showing your oil pressure. You're not guessing. Here's a tech tip. So if you have a vehicle with 0 oil pressure on the gauge, on your instrument cluster, 0 oil pressure, and yet your engine's running good and quietly, it's a pretty safe bet that it's the sensor that has failed. Because it'll be pretty obvious if the engine actually has no oil pressure. So we see this a lot where people are driving their car and all of a sudden they look down, or maybe a warning light pops on and they look down. Oil pressure is 0. They call me up, freaking out. My car is showing 0 oil pressure. What should I do? Can I drive it? Do I need to tow it? What do I do? What do I do? And I always say, okay, start your engine and listen to it. Does it sound okay? Yeah, it sounds normal. Okay, then don't worry. Drive it over here. Just drive it over here. Your engine's okay. It's the sensor that has failed. Because you guys are going to know an engine that has 0 oil pressure. It's going to be noisy and rattly, and it's going to be pretty obvious. Okay, so we are done with the sensors. Good work. We made it through. That was a lot of sensors to go over. We made it through. All right, so we're going to touch on some stuff about gasoline. So we're talking about gasoline. One of the things we talk about is octane, and you'll see that at the fuel pumps when you go to gas up. Octane equals the fuel's resistance to detonation. That's what octane is. Basically, how flammable is it? So you go to the gas pump, you see regular, mid-grade, and premium. What exactly is the difference? Guess what? Here's a big surprise that most people don't know. Higher octane burns slower. It's actually less flammable. Yeah, true story. So your premium gas is actually less flammable. I know, that sounds crazy. Your regular gas is going to be more flammable than your premium gas. Race gas, even less flammable than premium. So that blows a huge myth out of the water. One of the biggest myths that I hear is this: premium gasoline is better for your engine because it runs hotter and therefore burns cleaner. I've even heard this on a radio program once, or Car Talk or whatever. No, not true, wrong. So why do we need premium fuels? Here's why: because higher performance engines are going to require a larger octane rating or a less flammable fuel to avoid bad things from happening. For example, a Chevy Cobalt is going to take regular gasoline, while a Chevy Corvette is going to require premium. Kind of makes sense, huh? Also, turbocharge, supercharge, anything like that, higher performance, it's always going to take premium fuels. If you do not run premium fuels in these engines, we can get what's called pre-ignition, detonation, or spark knock, in other words, and we're going to talk about that in just a minute here. So we're going to switch gears here to talk about symptoms of an incorrect running engine. So we're first going to talk about an engine that's running too rich or too lean. For an engine that's running too rich, you're going to notice some black smoke out of the exhaust. It's going to have a real bad odor. It's going to stink. It's going to really, you're going to want to get away from standing behind the exhaust. And you're also going to notice that your eyes are going to start to water if you're near the exhaust. It's kind of weird, but all of a sudden, yeah, you're like, oh, that thing kind of stinks, and notice your eyes just start to water. That's because you got a rich condition. So that's all signs of a rich condition. If you got a lean condition, it's just going to have a really, really hot smell to it. You can also sometimes have a lack of power. So it's just got it's just going to smell like something's burning, really hot smell. Now we're going to talk more about that in the diagnosis module, but we're also going to talk about pre-ignition and detonation. Bad, bad, bad. So pre-ignition, what is it? Pre-ignition is when the air-fuel charge ignites before the spark plug fires. So let's say that again. your air-fuel mixture ignites or explodes before the spark plug even fires. That's usually caused by hot spots, which can be simple as an overhanging gasket or an incorrect spark plug, a metal burr somewhere in the cylinder head, or even excess carbon buildup on the spark plugs or on the cylinder or on the piston. Pre-ignition. Detonation is another common one, also referred to as spark knock, and that is a violent explosion in the combustion chamber rather than an uncontrolled burn, usually caused when the fuel is subject to too much pressure, too much heat, or both. So which is why we use premium fuels. Higher octane fuel can help counteract this. That's why we use premium fuels. This can also be caused by incorrect ignition timing. So spark knock can actually be heard while driving a vehicle. A lot of times I'll hear it if I'm doing like a wide open throttle acceleration, and it just sounds like it has kind of a ting 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 ting. You'll hear almost like a sharp metallic sound coming from somewhere, and that's actually spark knock. So we're actually hearing an explosion in the combustion chamber. So as you can imagine, that can't be good, right? What can that do to an engine? Both of these conditions can cause cracked piston rings, cracked piston ring lands, and or the deterioration of the top of the piston. Because remember, instead of a nice slow controlled burn, we have explosions, violent explosions happening in there. So we don't want that. Well guys, we did it. We just covered a lot of stuff there, and now you know not only how an engine runs, but how we control that engine and make it run perfectly. So well done. Hope your brain's not smoking too much, but we took a lot of information there and we made it easy, didn't we? So good job. Next module, module 10, we're going to talk about the diagnosis process. So again, what makes the difference between a mechanic and a technician? Remember, a mechanic is a part swapper and a technician is a problem solver. Which one do you want to be? So in module 10, we're going to give you a step-by-step process to properly diagnosing vehicle issues. So I can't wait to go over it with you, and we'll see you then. Beep, beep.
Not beep beep.
Not beep, beep.